Okay, so let's continue from where we left off, which what we did last time is we started talking about the A sub something, E sub something, and EQ sub something. And in this particular case, we were talking about the Turing machine versions. And what we found last time is that ATM is undecidable, so no algorithm can decide ATM. And ATM bar is, uh, actually, I should say, ATM is undecidable but recognizable. So it's recognizable because we can just simulate the machine. ATM bar then is uh, unrecognizable. So there's not even a recognizer for ATM bar. Okay, so we tackled the A problem, so let's tackle the E problem. So ETM here is all the machines. So M is a Turing machine, and L of M is empty. And we want to check um, whether the Turing machine's language is empty. And the thing is, well, we saw that ECFG was decidable, so ETM could go either way. So what we'll be proving here is that it's undecidable. And in fact, pretty much every problem that you'll ever find, as we'll see soon, is undecidable. So how do we actually use this? So the thing is, well, we could go through a long undulating proof like we did for ATM, like last time, but I don't really want to do that. That just seems like way too much work. So what we'll do here is we're going to, so here's the idea and how we will go for some of these results, but then we'll get even easier than this. So the idea here is um, suppose ETM were decidable, and so we assume that it can be decided, then we will get a supposed based on that based on that supposition, we'll get a supposed decider for a known undecidable problem or language, I guess. So the only one that we know of that we already know to be undecidable is ATM. I guess we could do ATM bar also, but we'll do it with ATM. So how's this gonna work? So let's just, so here's the proof of this. So let's suppose that E is a Turing machine that decides ETM. So remember that any decider for ETM must take a Turing machine and nothing else and determine whether or not its language is empty. So now we're going to try to decide ATM based on this hypothetical decider E. So remember the ATM problem takes a machine and a string. So we're trying to decide ATM here. So on input MW, where M is a Turing machine and W a string. So what do we do here? Well, if I feed the machine M that we got into the decider E here, well, if the if the decider E says, yeah, M's language is empty, then there's no way that M could accept W because E said M's language is empty. But so that's all fine and good. But now suppose that E says, no, your language is not empty. And that's the only information that E could tell us, that its language is not empty. Well, just because it's not empty doesn't tell us that M accepts W. It accepts something, but it might not accept the string W. So we can't just feed the machine M into the machine E to figure out whether its language is empty. So here's the critical idea. So what we're going to do is we're going to construct a Turing machine. I'm going to call it M prime. And the goal of this machine M prime, it's going to have two behaviors depending on whether M accepts W. So whether the original machine M accepts the original string W. Well, if I'm going to make a Turing machine, well, it could take anything as input. So let's just say that it gets some input X. Okay? So it gets some input X, and it could be totally different than W, but it's just some string. It could be anything. So what are the two behaviors going to be here? Well, what we want here is we want the fact of whether this M's language is empty or not to be coinciding with whether or not M accepts, sorry, I said that wrong. Whether or not M's prime's language is empty should coincide with whether M accepts W. So, in other words, we want M prime's language to be empty if M accepts W, or the other way around. And if M prime's language is not empty, we want the other condition to happen. So here's how this is going to work. So the first step is if X is not equal to the string W, which we were fed up here, so if it's not equal to it, reject. So just reject it immediately. But otherwise, if X is equal to W, so the only case of whether X is equal to W, then run M on W. And if M accepts W, then we will accept. Okay? And you may be thinking, okay, well, you can't do this step right here because M could run forever, and you're completely right. It could run forever. But all we're doing in this step is constructing the machine. We're not actually running the machine. So once we have made the machine, we can actually feed it into the supposed decider because the decider will take any Turing machine and will always halt in a finite amount of time. Guaranteed, because that's what a decider does. So we're going to run E, that supposed decider for ETM, on input. Now we're going to feed it M prime. So what are the two behaviors? Well, if E accepts, which means that the language of the machine we just made is empty. So what does that mean? Well, if M prime's language is empty, then no point in here did M prime accept X. It never accepted any string. Well, no matter what happens, it rejects every string other than W, for sure. It rejects every string. But so now let's look at the case down here. So if it is equal to that string, well, the only possible way that the language could ever be not empty is if M accepts W. So if M accepts W, then M prime's language is not empty. So let's see. Well, here we're saying E says yes, which means M prime's language is empty, which means that M prime does not accept W, so we reject. You don't have to put that M prime does not accept W bit there. That's just so that we understand everything that's going on. So the only way that the Turing machine's language, M prime's language, is empty is if M does not accept W. And we're trying to decide the ATM problem, which is determining whether M accepts W. So then if E rejects, and here that means that M prime's language is not empty, oops, no curly brace there, then what happens? Well, it rejects every string other than W. Well, so that means that the only possibility of being a non-empty language is if it accepts W, which means that we had to hit this final step here of whether M accepts W. So this means, oops, I should have M does not accept W there. That was my mistake. M does accept W, so we accept then. And it is possible that we achieve the opposite answer that the machine E says. So we could finagle the M prime machine to do the opposite, but here we happen to get the opposite. So let's just run through this again. So we're making a machine that has two behaviors, whether or not M accepts W. It has whether its language is empty or not depends only on whether M accepts W. So we're just making the machine in step one, which we can do. We're just constructing the machine. We're embedding the instructions right into the machine. Just writing out the instructions right on the tape. So then step two, well, we suppose that there's a decider for the emptiness problem for Turing machines. And since it's a decider, it must say accept or reject. So then we achieve a conclusion about whether the original machine M up here accepted W up here. And let's see, well, step one takes a finite amount of time because we're just constructing the machine. Step two takes a finite amount of time by supposition because we had a supposed decider. And step three and step four obviously take a finite amount of time. So since ATM is undecidable, then ETM is undecidable. Cool. So the only way we could have ever made this decider for ATM is based on the assumption that E was a decider for ETM. Cool. So let's go on to the next one, which is EQTM. So here, as you might expect, we have two Turing machines. So M1, M2 are Turing machines, and the language of M1 equals the language of M2. And you wouldn't be surprised to know that this is undecidable. So how do you actually do this? Well, you could do a transformation, if you like, from the ATM problem like we did before. Like we suppose that EQTM is undecidable, and then we tried to decide ATM just like we did before. But we don't have to choose ATM if we don't want to. We could choose ETM if we want to. And it turns out that using ETM is a lot easier in this case. So let's suppose that E decide. Oh, no, sorry. So here we got to get the order right. So let's suppose that D decides EQTM. So remember, we're trying to solve or decide an already known undecidable problem. I can't say about whether EQTM is undecidable because I haven't proven yet. But we have proven that ETM is undecidable, so we can try to decide it based on a supposed decider for EQTM. So let's try to decide ETM. So remember, ETM takes exactly one Turing machine. Let's call it M, where M is a Turing machine. So what do we do here? Well, we want, again, so here, the decider D here has to take two Turing machines. And well, let's see. Well, let's all we're trying to figure out is whether M's language is empty or not. But we have an oracle, if you like, a magic crystal ball that tells us whether two Turing machines have the same language. Well, we could just make a machine that has empty language and have that be the second machine. So let's let T be a Turing machine with empty language, and then run D, the supposed decider for EQTM, on the two Turing machines, the one that we were given and then the one we made, so M and T. So let's see, if D accepts, well, let's see, if it accepts, then that means that M and T have the same language. Well, T has empty language, so that means M has empty language. But that's the problem we're trying to decide. So here we should accept. And then if D rejects, well, that means that M and T don't have the same language, which means that M cannot have the same language as the empty set, which means it must accept something. So because we're trying to decide the emptiness problem, we need to reject here. And clearly, step 2 runs in a finite amount of time because D is a supposed decider for EQTM, and T we can just construct really easily. Step 3 runs in a finite amount of time too. So since ETM is undecidable, then EQTM is undecidable too. Cool. So let's see. So where are we at now? Well, here we could do something like this, where we suppose a machine, a language is decided by something, and then try to decide an undecidable problem. And we could do that, but it turns out that there's a much, 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 much easier way of showing a wide class of problems that are undecidable. It doesn't show everything undecidable, but it shows a wide class of them. So to introduce this, I need to talk about properties of Turing machine languages. So what in the world is that? So a property of, so this is a long definition, property of Turing machine languages, I'm going to call P, is a set of Turing machine encodings. So just like ETM is an example of this. So that for any two Turing machines, I'm going to call them M1 and M2. So any two Turing machines, they can be anything, but with a certain property, which is that they have to have exactly the same language. So if we take any two Turing machines at all, and they happen to have the same language, then either one of two conditions occurs. So either 1 or 2. So for the first one, it's either the case that both machines written as strings are in this property here, P, or in the language P, if you like, or both of them are not in P. So an example of this. So let's talk about ETM. So if we have two Turing machines, two any old Turing machines, M1 and M2, with L of M1 equal to L of M2, then what we should always be asking is, could it be possible that one machine is inside ETM and the other one is not in ETM? And the answer is no, because they have exactly the same language. Either both are empty or both are non-empty. Because the only criteria, if you like, of being in the ETM language is you have empty language. I don't care anything else about what the machine does. As long as you have empty language, you're in there. So then for that reason, ETM is a property of Turing machine languages. So an example of a property, sorry, not a property, a language, not a property. So I'm going to call it ETM prime, and that's similar to ETM. So M is a Turing machine with L of M equal to empty set. And so now this second condition is going to get us here. And M has at least 7 states. It doesn't have to be 7 here, but the key here is that we're introducing something that is not, it doesn't have anything to do with the language itself. So it's about how the machine is made. It has 7 states at least. So here, if you have 2 Turing machines with the same language, then it is possible that one of them is in ETM prime and the other one is not. Because one of them could have more than 7 states and the other one could have fewer than 7 states. So ETM prime is not a property of Turing machine languages, whereas ETM, the original one, is a property of Turing machine languages. And then one more definition is a non-trivial property has at least one Turing machine inside it and at least one Turing machine outside it. Oops. So it just means that there is a Turing machine inside that that property, and there's one that's not in, that doesn't have the property. So ETM is an example of a non-trivial property. Well, we proved that it's a property, and think of the Turing machine that rejects everything. Well, that's in ETM because it has empty language. Now think of a Turing machine that accepts everything. Well, that's not in ETM. So that means that ETM is a non-trivial property. So an example of this is ETM. An example of not non-trivial is, I'm going to call it sigma TM. I just made that up, which is all the Turing machines. So M is a Turing machine with a language. And we think, what? Well, every machine has a language, so that means that every Turing machine is inside sigma TM. And there's no Turing machine that's not inside this inside sigma TM. So this would be an example of something that is not a non-trivial property. Why the distinction? Because for this language, we can decide it because it has every Turing machine in it. So if you get a Turing machine, it's in that set. So therefore you will always accept, which means that it is decidable. So this one is decidable. And conversely, if you have a set with no Turing machines in it, then when you get a Turing machine as input, you just reject it because it's not in the set because there's nothing in the set to start with. So there's a reason that we are talking about non-trivial here. So now for the big boy theorem, which is called Rice's theorem. It's not about Rice. There's a famous mathematician whose last name is Rice. I commonly remind students to apply Rice's theorem by telling them, like, hint basmati or something. So what does Rice's theorem actually say? It says that every, and it really is every, non-trivial property of Turing machine languages is undecidable. So every single one. So ETM is undecidable. Like all TM, where we look at the Turing machines that accept everything, that's undecidable. If we think of a language where we have all Turing machines that accept exactly 3 strings, that is also undecidable. Every single one is undecidable, which is pretty amazing. So let's see how to actually apply Rice's theorem, and then we'll actually prove Rice's theorem in a bit, if we have time, I guess. So let's talk about this language right here. So you may wonder, well, do we need all of the power of Turing machines? Could it be that I just have like a computer program that I could just I can just easily make a DFA for, so instead? So maybe like the Turing machine is way overpowered for the problem that we're interested in. So this is kind of going toward that direction. So I'm going to call it regular TM. And it's the set of all Turing machine descriptions, where M is a Turing machine and the language of M is regular. So there is a DFA for it. Oh, and one thing I should mention. When I say property of Turing machine languages, um, you have to have the language be something of the form single machine and nothing else after that. So I can't have, like, say, MW where something happens. Or I can't have 2 machines written side by side, because it's about the language of one machine versus the language of a completely separate machine. Like in this case, M1 and M2 are, in this part right here, are inherently related to each other. They're presented together as input. We're only talking about languages that have a single machine description for each of the strings. So we couldn't use Rice's theorem to prove like EQTM undecidable or ATM undecidable. We can use it for ETM, but we can't use it for like ATM or EQTM. So right off the bat, well, it seems like we could apply it for regular TM. So how do we actually prove that this is undecidable? What we have to do is to show 2 things: that it's a property of Turing machine languages, and 2, that it's a non-trivial property. So then once we prove those 2, then by Rice's theorem, regular TM is undecidable. So let's see. Well, what does a property of Turing machine languages say? Well, it says if we have 2 arbitrary Turing machines, M1 and M2, that are the same language, then could it be the case that one of the languages is regular and the other one isn't? Well, that's not possible because they have the same language. So either both are regular or both are not. So it is a property of Turing machine languages then. Non-trivial. So in non-trivial, we have to give an explicit example of a Turing machine that is in regular TM, and an explicit example of a Turing machine that is outside regular TM. So one common example students pick, and it's perfectly fine, is I'm actually going to call it something else other than M1. Let's call it X. Be a Turing machine that accepts everything. So it just accepts all strings. Well, its language is sigma star. Well, that's regular. So that implies that X, the string encoding X, I guess, is in regular TM. Cool. So now we got to find an example of a Turing machine that has a non-regular language. So what's an example of this? Let's let Y be a Turing machine that has language in our favorite non-regular language, 0 to the n, 1 to the n. And it's pretty easy to make a Turing machine that has this language. And this implies that Y is not in regular TM. So then the most important part, by Rice's theorem, regular TM is undecidable. So whenever you want, so one thing that should be pretty obviously clear, if you can apply Rice's theorem, please do it. It's way easier to use Rice's theorem than to do the work that we did before, like with ETM and ATM and all that jazz. Use Rice's theorem whenever you possibly can. It'll save your soul, I swear. It is a godsend. So please use Rice's theorem. And in this case, we can. If we're given a problem like EQTM, for example, we can't use Rice's theorem, and then we have to use other techniques. But if you can apply Rice's theorem, please do so. Okay, so what I'm gonna do here is I'm actually gonna cut it short because I wouldn't be able to fit the proof of Rice's theorem within 17 minutes, which that's what I apparently have left. So I will be proving Rice's theorem for the next lecture, so I'll see you then.